Apart from the voltage and current waveforms, we also need to look at certain other aspects of a power converter. It is good to have a wish list for the characteristics of an ideal power converter. We'll start with the waveforms. The converter should have ideal AC and DC voltage or current waveforms on the input side as well as the output side. For example, consider a rectifier, which is an AC to DC converter. So this is an AC to DC converter. There are some elements within this. There are some circuit elements within this box which are connected to realize a rectifier. And the input voltage is usually sinusoidal because that is what we get from the utility or grid. So this input voltage is sinusoidal. So V in is sinusoidal. We need the output voltage. We want the output voltage to ideally look like this. And we also want the input current to look like a pure sinusoid ideally. And on the DC side, usually the loads are resistive, so the output current will also be constant because the output voltage is constant. But why do we need such clean waveforms? It can be explained from the viewpoint of the average power transferred, and it will be discussed later in this course. And then the second characteristic is that the converter should have 100% efficiency. Whatever power that is supplied at the input should be delivered to the output. That means there should be no power loss. And then the converter should work under all ambient conditions. Power electronic converters are required to be used in a variety of ambient conditions. Extreme temperatures. They are used even in space as a part of the satellite power system. Many power converters used in the industry have to operate under dusty environments. So the power converter should work under any given ambient condition ideally. And the voltages and currents should be regulated. That means there should be no change in their magnitude and or frequency under any operating condition. And we should be able to change the output voltage or current instantaneously as desired depending upon the circuit conditions. For example, consider that there is a load resistor that is connected at the output of this rectifier. And let us say that the current in this resistor, that means I out, it needs to be changed. And that means that the DC output voltage V out needs to be changed. And we would like to do this as quickly as possible. In the ideal case, we would like to do this instantaneously. The voltage and current waveforms should be insensitive to disturbances. Again, considering the rectifier circuit, if there is a sudden change in load, for example, say this resistor is variable and we have suddenly changed the value of the resistance. So the load is changed. The output voltage should not become low or high. It should be maintained at the desired level irrespective of the load changes. The power converter should not interfere with the other surrounding equipment. This is about electromagnetic interference. We know that a current is always associated with a magnetic field, and the same is true with the currents flowing inside a power converter. So the magnetic fields produced by these currents should not cause undesirable effects in the equipment which are in the immediate vicinity of a power electronic converter. The power flow should be bidirectional. This is a preferable choice. If we consider the AC to DC converter, we should be able to transfer power from the AC to DC side or DC to AC side. The bidirectional power flow is of importance in battery charging and discharging circuits. If a power converter has the capability of bidirectional power flow, it can be used for both charging and discharging a battery. That means to store and retrieve energy. This bidirectional nature is also useful in regenerative braking of a motor. When a power converter is connected between a source and a motor, the kinetic energy of the motor while braking can be fed back to the source if the power converter has bidirectional power flow capability. And it is always good to have a power converter with small size, small volume, and lightweight while meeting all the other performance requirements. However, in reality, the electronic converters will have limitations on all of these characteristics. The waveforms will be non-ideal as discussed previously. There will be power loss in the elements of the power converter, and the converter works only in certain range of ambient conditions. The response time becomes finite and the insensitivity to disturbances becomes limited. There will be electromagnetic interference and additional circuit elements have to be added to a power converter to make sure that the surrounding equipment are not affected due to this interference. All the power converters need not allow power transfer in both directions, and in many cases size reduction of a power converter becomes a big challenge. So having these characteristics of power converters listed, one can come up with ways to quantify and compare the performance of different power converters based on the above characteristics. For example, we can compare the performance of two types of AC to DC converters in terms of their output DC voltage waveform, input AC current waveform, efficiency, response time, and so on. In this course, our primary focus is on the first characteristic, voltage and current waveforms at input as well as output of a power electronic converter. We aim to answer this question for a given power converter. How close are the voltage and current waveforms to their ideal counterparts? To answer this question, we need to understand the reason behind the shapes of voltage and current waveforms in the various power converters, and that involves understanding the operation of a power converter in different time intervals. We will also have limited discussions related to the efficiency or estimation of power loss in a power converter and the size of a power electronic converter.